Okay, yeah. So you're the limitation that you do not provide a solution when decoupling does not work. What does that mean when decoupling does not work? That means that either that you don't find an optimal set of contracts either for to solve the moral hazard problem or to solve the adverse selection problem.
Great. So let me clarify on that. We can find the optimal contracts for just moral hazard or just adverse selection. That would be part of the standard that we had before.
Yeah,
The tricky part are those double deviations. What IMC guarantees us is that when we solve the decoupling, we are guaranteed that no double deviation will matter,
yeah,
that no one wants to double deviate. When IMC doesn't, or neither single crossing is satisfied,
I see.
there are double deviations that could be binding there.
Uh-huh.
So we still will have a solution for the decoupling. We'll just not be fully sure whether that solution satisfy all those potential double deviations that we are not considering. They're exactly the tricky ones to consider.
Huh. Okay.
So our problem is more we approach it, we see the solution, and then with that solution, we can say whether that problem, that solution to our decoupling procedure is optimal in the full-blown problem or not.
Okay.
If it is not, if it does not satisfy those conditions, we cannot guarantee that there wouldn't be a double deviation.
Okay. And if you cannot guarantee that there's not a double deviation, what does that look like for the individual moral hazard and or uh, adverse selection problems? How does that express itself in those the separate problems?
So good. So for the separate problems, we do have conditions from the literature on how to deal with them. So that wouldn't necessarily matter. What it makes a difference is one of the conditions for the adverse selection, let's focus on that one. I think that's the cleanest relation, is that you need to recommend, you need to require higher effort for higher types.
Yeah.
That is the monotonicity condition that appears in incentive compatibility. That's what you need for just pure adverse selection.
Yeah, you need right was
When you
incentive
have,
compatibility and participation constraint. Those need to be satisfied, right? So those could be
yes,
satisfied. You could solve the moral hazard problem, but you can't solve the joint problem. That's what you're telling me. It's possible.
yes,
Yeah.
yes. So let's consider the problem that we have only adverse selection. So what I observe is your effort. So I can condition how much I pay you on your effort on that A. And the incentive compatibility condition can be characterized by two other conditions. One is an envelope condition. Your utility needs to grow on type in a certain rate. The second is a monotonicity condition, which means I need to require higher effort from higher types. I cannot ask someone that is more skillful than someone else to exert a lower effort. That wouldn't be incentive compatible.
Yeah.
That monotonicity is enough. You just need a simple monotonicity. You don't need any increase in a certain rate to guarantee incentive compatibility when you have pure adverse selection. Once we add moral hazard there as well, that monotonicity becomes stronger. We don't need only to increase the effort, that effort level needs to increase faster than it cannot never be flat. It needs to be strictly increasing and strictly increasing at a certain amount.
Mm.
That's where the double deviation might start playing a role. It might be that I can fully characterize your contract with just adverse selection, but as soon as I don't observe your effort level, I only observe your output, you might say that you are a very low type, get a different type of contract, and then adjust your effort very much in a different way that I didn't consider. The IMC and our Theorem 1 allows us to bypass those double deviations and say whenever those double deviations won't matter at all, and we don't even need to check them.
Mm.
So that's usefulness of this theorem is avoiding us checking all these potential double deviations.
Okay, yeah, thanks.